Let's study 9th standard ICSE Physics, Chapter 4b, Atmospheric Pressure. All fluids exert pressure. Even the atmosphere exerts a pressure, the air pressure. The thrust exerted per unit area on the Earth surface due to the column of air is called atmospheric pressure on the surface of Earth. So if this is the surface of Earth and you are here, imagine the layers of air directly above you. The entire pressure of this is on your body. In fact, the total air pressure on your body is equal to that of around a couple of elephants on your body. That's right. But we are not aware of this because we have blood pressure inside us. And this blood pressure is acting opposite to the air pressure. It is outwards, whereas air pressure is trying to crush us and the blood pressure is trying to inflate us. So we don't feel the air pressure. In fact, the blood pressure is slightly more than the air pressure. And that is what we measure using a sphygmomanometer. Now imagine if you are in space without the spacesuit. So there is no air pressure on you, you are in vacuum, but you still have the blood pressure. So you'll explode. Blood will leak out of your body. And that's what happens when you go on high altitudes, on top of a mountain, very high mountain. The air pressure outside decreases. So comparatively now, the blood pressure is too much. Hence, your nose may bleed. So though we can't feel the air pressure, to understand how powerful it is, let's do a very simple experiment. Take a tin can filled with some water and heat it so that the water boils and the steam goes out. And as the steam goes out, it drives away all the air inside it. Soon, with little water still inside, close the cap of the tin and cool the tin can by pouring some cold water outside. Now there is no air inside, there's only steam. This steam will now condense back into water. So the entire volume which was filled with steam now has a little bit of vacuum in it because the steam is now condensed into water. And if there is a partial vacuum inside, the internal air pressure has now decreased drastically. You see, initially there was air pressure internal which balanced the air pressure external, due to which there was no change in the integrity of the tin can. But as soon as the internal air pressure decreases, now the external air pressure is comparatively greater. No, the external air pressure doesn't increase, it's the same, but now it is comparatively greater, which will crush the tin can. Just imagine, you're not even touching it and let the air pressure do its work of crushing it. This shows how powerful air pressure is. Even when you're sucking a drink with a straw, you're actually using air pressure to your advantage. What you do is, you are sucking all the air from inside the straw. You see, initially, the straw had air inside and of course there is air outside. So the internal air pressure and the external air pressure is the same. But if you suck in all the air from the straw, what is left inside the straw? A partial vacuum. So this will decrease the internal air pressure. So now the external air pressure, who was waiting for this opportunity, will win. And it will push this drink into the straw and up it rises and down it goes into your mouth. So actually you are not drinking this liquid. You are just sucking air. It is the external air pressure which is forcing this liquid down your throat. That's why in vacuum or in space, if you try to drink with the help of a straw, you won't be able to, because there is no air pressure to come to your rescue. Now let's understand the action of a syringe. This can be a syringe used for injection or to just play. Initially the plunger was here. When you pull the plunger up, and assuming it is airtight, a partial vacuum is created in it. Let me draw this for your understanding. So initially it was here and now you've pulled it here. So what is there inside here? Nothing. It's a partial vacuum. So if the internal air pressure is far less than the external air pressure, then of course they won't crush this plastic syringe. Instead, the air pressure will push the liquid into the nozzle and up it rises to fill the vacuum created by you. So that's how you fill a syringe with liquid. Similarly, even fountain pen is filled with ink. You have a rubber tube, you press it so that all the air inside is expelled out, and when you release the rubber tube, there is a vacuum inside. So what happens is the ink is sucked into the refill. Next, action of rubber suckers. You may have seen such rubber suckers which can be stuck on flat surfaces like on tiles and marbles or even on a mirror. How does it work? Well, initially the rubber sucker was something like this. There was air inside and there was air outside. They balanced each other. But when you press it against this wall, all the air is forced out. So there's nothing left in between. And now when you release it, so first of all you've pressed it, so it's become flat. And now again if you release it, then again it will regain its position. But this time there is a vacuum out here. And if there is a vacuum here, then the external air pressure being far greater will hold this rubber sucker onto the wall. It's as if the rubber sucker is stuck to the wall for a long time. Next, action of a siphon system. Imagine if you have to transfer one liquid from one container to another. Especially this is useful to transfer petrol or diesel from one vehicle to another. Now this is called the siphon. But how will it be transferred? Yes, if the liquid is at point C, it can easily fall down into this beaker due to gravity. But how can we raise this liquid up till point C, up till height C? There is no motor to push it up. There is no pump to push it up. So what we'll do is, first of all, take the siphon in your mouth and the person will suck some of the air in. And when the person sucks some of the air in, he's creating a partial vacuum out here, due to which the external air pressure will now push the liquid into the siphon till height H, till height C, and now quickly move this other end into the other container, because now the liquid will start flowing due to gravity. And this process will now continue. The air pressure will keep emptying this beaker, and this beaker will start getting filled up. It just needed an initial boost by you. Initially you'll have to suck in some air and then let air pressure do the rest of the job. Next, taking out oil from a sealed oil can. Often, if there's an oil can completely filled with oil with no air inside, and if you make a tiny hole on it, now if you tilt this can and try to remove some oil from the oil can, it won't come out because of the air pressure from outside. The air pressure will hold the oil in. So what we need to do is we need to make a second tiny hole. Then it will be able to come out, because now air will push from one side and pushing the oil out from the other side. Measurement of atmospheric pressure can be done with the help of a barometer. A simple barometer just has a mercury column in it, and the height of the mercury tells us what is the air pressure outside. Here there is a vacuum on top called the Torricellian vacuum. Usually the height of the mercury is around 760 millimeter of mercury or 76 centimeter of mercury at sea level. If the outside air pressure increases, then more mercury will be pushed into this tube and the height of the mercury will increase. On the other hand, if the outside air pressure decreases, then the weight of the mercury will be strong enough to make it decrease its height. So you see, the height of the mercury will tell us the air pressure outside. The construction and the working is not in syllabus. Again, this page is entirely cancelled. But there are some issues with this barometer. First of all, it's open, so some impurities can fall into the mercury which will hamper accurate measurement. Secondly, it's very difficult to transport it from one place to another because mercury may just spill over. It's not portable. So we have an improved barometer called 14 barometer. Now let's just understand the diagram for knowledge sake, although we don't have to study it in detail. The benefit of this is that it is completely closed, so there is no chance of contamination from outside impurities. And the principle is the same. If the outside air pressure increases, then the mercury level will increase. It even has a vernier scale, so it will give us a more accurate reading. And finally, we have the aneroid barometer. The aneroid barometer is the best version because it does not even need mercury. It has this box B, which has nothing inside. It's just vacuum. It is connected to the rod, which is connected to the wheel, which is connected to a pointer, and there is a circular scale. Now, if the external air pressure increases, then it will compress the box B further, which will move the rod down, which will turn the wheel, and this pointer will also be turned towards the higher measurement. And if the external air pressure decreases, then the box B, which is quite elastic, will expand, moving this pointer towards the lower scale. So that's how we can know the external air pressure. Now, what if we change these values of air pressure with the height? We know that as we go higher and higher, air pressure decreases. So at sea level, it is 76 for sure, 76 centimeter of mercury or 1 atm. And let's assume that with every 10 meters or 120 meters of ascent, whenever your height increases from sea level by 120 meters, let's assume that the air pressure decreases by 1 centimeter or 10 millimeter of mercury. So if the air pressure shows as 75, I can mark this as 120 meters. Then 74 will be 240 meters and so on. So actually I can convert this aneroid barometer into an altimeter. That is a device which tells me the height. I can use it in aeroplanes, etc., where indirectly I can know the height at which I am because that corresponds to the air pressure. Another use of the barometer is by knowing the air pressure, we can predict the weather. More about that shortly. But let's first understand why the air pressure decreases as the height increases. Well, there are two reasons behind it. First of all, when you go on top of a mountain, the height of the air column above it is less. Let me give you an example here. This is the plane and this is the mountain. You are here. So you have such a tall layer of air acting on you. The air pressure is more. And if you are on the top of a mountain, then the height of the air column above you is less. So the air pressure is less. Second reason is that the density of air also decreases as you go up. We know that air is rarer on top, and less the density of air, less will be the air pressure. So both these factors mean that as your height increases, air pressure decreases. The graph shows the change in air pressure with height. You can see that it is non-linear. That is, the change in air pressure is not equal for equal intervals in height. That is why mountaineers have to carry air cylinders or oxygen cylinders, because the air pressure as well as the density of air is very less on top of a mountain. And fountain pens will leak on top of a mountain, you see, because at a great height, the air pressure outside is very less. So the ink inside the fountain pen will leak out. That's why the ball pens were invented, so that pilots and people traveling by aeroplanes can carry a pen without worrying about the leakage due to low air pressure. Now, how can we predict weather by looking at the barometer? There are 5 ways. First, 5 scenarios. If the barometric height, that is the air pressure, suddenly falls, means air pressure suddenly falls, that means that there could be a storm or cyclone approaching. If the barometric height, that is the air pressure, gradually falls, it may be a signal of rain. If there is a gradual increase in the atmospheric pressure, it means there is dry weather. If there is a sudden rise in the air pressure, then it means extremely dry weather, because means that it's a high pressure area surrounded by a low pressure area. It's like an anticyclone. And if there is no change in the air pressure, that means that there is no change in the weather. But how can air pressure tell us anything about rain or dryness of the weather? Well, you see, when the air is very humid, full of moisture, the density of air is less. That's right. Humid air has less density. Water vapor has less density than the usual air. And less the density means less is the pressure. That's why if you see a decrease in air pressure, it means there is possibility of rain, because it means that humidity has increased. Now, in the salt examples, the fourth salt example is cancelled. And there are 5 numericals which are pretty easy. Let me teach you the third and the fifth one. The third one, mark the fifth one as IMP. The third one, at sea level, the atmospheric pressure is 76 centimeter. And for every 120 meters of ascent, air pressure falls by 10 millimeter. Now you're on top of a hill and the air pressure is 70 centimeters. What is the height of the hill? Well, we can solve this by unitary method. For 120 meters of height, the pressure difference is 10 millimeter of mercury. And we have 76 minus 76 centimeters, that is 60 millimeters of mercury is the pressure difference. So what is the height? Now you can cross multiply and get the answer as 720 meters. And they've asked us to state the assumption. You have to assume that it falls linearly, which is practically not true, but here we can make that assumption to get an approximate answer. Linearly means that for every 120 meters, it always falls by 10 millimeter fixed, which is not correct. But in this sum, this is the information given. Now the fifth sum, assuming the density of air, given, find the fall in barometric height in millimeter of mercury at a height of 107 meters, height is given, and the density of mercury is also given. So we'll start with the equation that pressure 1 is equal to pressure 2. Here pressure 1 is the pressure indicated by the mercury level, barometric height, and the pressure 2 is the actual atmospheric pressure. They have to be equal because the barometric height pressure indicates the air pressure. The formula of pressure of any fluid is H rho G is equal to H rho G. G and G cancelled. Height 1 is the height, the barometric height, and that is what is asked. Fall in barometric height will be H1. That's the unknown variable here. Rho 1 is density of mercury given in SI units. Great. H2 is the actual height in air. In air, the height is 107 meters above sea level. So 107 meters, it's in SI unit. And the density of air is also given in SI units 1.295. So no need for any conversion. I want H1 alone. This goes down, solve and get the answer. You'll get the answer as 0.001 meter. No, actually 0.01 meter, which you should convert into millimeter. Now let me explain the first sum as well. Convert 1 millimeter of mercury into Pascal. So here we'll use the formula pressure is equal to H rho G. But all of them should be in SI unit because they want the answer in SI unit Pascal. So the height is 1 millimeter, convert that into meter, that is 0.001 meter. Density is already in SI unit 13.6 into 10 raised to 3. And G's value is also given as 9.8. So now multiply this and get the answer as this. Do not just copy the answer. Practice how to calculate the decimals and the exponents. That is very crucial.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.